Hello, Toru.
Hi.
And Justice, what's going on? I have a new swivel chair. If anyone noticed, taking advantage of it, no one complimented me on my new swivel chair.
Nice chair.
Thank you, Toru. See, Toru's catching on. There we go. Toru, do what I tell you, you'll go far in life, as far as I am, which is. Herman Justice Safa?
Can't really see your chair.
What do you say?
Can't really see your chair.
Oh,
You just see you
okay.
spinning.
Who can guess what kind of chair I am sitting in right now? It's a swivel chair, more specifically.
Is it the one Thomas Jefferson made originally, his original design?
I was just thinking about that the other day that Thomas Jefferson made the swivel chair. How awesome is that? You know, he also invented like the first industrial pasta machine in America. He just wanted pasta. It did too much for a handmade paste. Check this out. It's like a 50s diner stool. It's pretty sweet. But anyway, that's my setup over here. How's it going with you guys?
Pretty good.
Thumbs up from Herman. Tori will give a verbal thumbs up.
Yeah.
Offers in the house. Cool. Well. If no one's anything else to say, I have a ton to say. I have 3 pages today. We're gonna move because this is a very exciting topic. We're almost in direct proofs. Tomorrow we start section 4.1 where we get into direct proofs. It's our last day of laying the groundwork, and then we can actually start to prove things. It's gonna be awesome. I feel like it's not gonna like you know it's gonna be awesome because I'm gonna take a bunch of time to tell you how awesome it is. But we've gone so slow and thorough. I feel like it might not even seem special. I might say, like, oh, obviously, but it's special. Like if you think about where we started in August, wow, oh my God, it's almost October. We started in August. We are now. We've kind of come a long way. There's a lot of notation now that we're using. But anyway, welcome everybody to Discrete Math. This is. Here we go. This is going to be section 3.3. Got it. Nice. Yeah, by the way, my whole experiment with the other camera setup, we're abandoning that for now. That was way too small. I had way too less, not enough space at all. But today, we're going to do section 3.3, and oh, there we go. Section 3.3. And I want to start off with talking about this whole what it means for things to be equivalent thing, because I don't like the way I described it the other day. It felt long-winded and just convoluted. So I'm going to put that issue to bed right now. And the way we're going to talk about that is let's talk about what it means for things to be equal in like algebra, and then we're going to see a bunch of analogies. So for example, in algebra, if we define A, or I'll say X, if we define X to equal 1, then X equals X squared, right? Because 1 equals 1 squared. We good? I feel like we're good with that, right? But in general, does X equals X squared?
No.
No.
But obviously not. For what was the question? What were you gonna say?
No, for negative x.
Oh, yeah, perfect. Exactly. Right. For no negative x's, we would use 2. Right. So for example, x equals x squared. No. X is not equal to x squared. In general, say example, x equals 2. So the point is, like, if we actually define the variables here, if we actually define what x is, right, then x equals x squared this just means evaluate left and right sides and see they're equal, right? So if we actually define an x, right, saying that the left side equals the right, like saying we have an equality just means that the number the left side equals the number the right side equals, right? But in general, what this means is equality must hold for any values we plug in, right? So in algebra, right? If we're in general, if we don't define what x is, saying an equation's equal, saying it actually works, is saying that it works all the time. So an example, one of those is example in general, x minus 1 times x plus 1 does equal x squared minus 1. Because it works for all possible x, not just some x you plug in, like x equals x squared, all possible x. That makes sense, right? Good. So the point is that we have to be careful with thinking about things in general versus thinking about specific things. Because it's not always wrong that x equals x squared, but in general, x is not equal to x squared. All right. So we can see that in logic too. So in logic, right, P and Q does not equal P or Q in general, right? If you can see, it doesn't equal that in general because, example, if P is true and Q is false, then P and Q is going to be true and false, which is false, while P or Q is going to be true or false, which is true. So true does not equal false. So in general, this equation doesn't hold, right? However, for specific P and Qs, like P equal true and Q equals true, right? Here, P and Q does equal P or Q, because this is true and true, which is true, and this is true or true, which is true. So even though this doesn't work in general, right? Like in general, this is not like a logic law we have, right? These are not equivalent expressions in general. Even though it doesn't work in general, sometimes it'll work if you have the right P's and Q's. All it's saying is that P and Q and P or Q are different. They are different statements, right? Just because they are different statements doesn't mean they can't sometimes doesn't mean they can't sometimes have the same value. For example, saying that like I like grilled cheese, right? And saying that the sun is made of hydrogen and helium, right? Those are both true statements. Do they have anything to do with each other? No, they're unrelated, right? For another person, maybe you don't like grilled cheese, but another sun is still going to be made of hydrogen and helium. So the point is, they're just unrelated. Sometimes they'll line up, sometimes they won't. They're just unrelated, different, right? That's what being not equivalent means in general. So sometimes they'll be the same though, sometimes they'll be different. Make sense? Okay, so now to bring this up to the big boy level with predicate logic, got ahead of myself, trying to combine a P into an R to make a PRAR. I misspelled logic. This is embarrassing. Okay, we're starting over. predicate logic. I was never good at the spelling C's in school. I mean, spelling B's. See? So the point is, so predicate logic, what we just talked about last time is that the universal conditional is not equivalent to the universal converse. So what we showed last time is that for all x and d, P of x implies Q of x is not equivalent to for all x and d, Q of x implies P of x, right? These are just straight up different statements. Just like saying, I like grilled cheese and the sky is blue, right? They are just different things. Sometimes they're like saying X likes grilled cheese and the sky is blue. Sometimes someone likes grilled cheese and the sky is blue. Sometimes someone doesn't like grilled cheese and the sky, it's dark time. It's like dark time. This feels like a Game of Thrones or something. Sometimes it's nighttime and it's dark out and the sky is not blue. It's like black or whatever. So the point is, these are just different statements. So this equality, or not equality, this equivalence does not hold in general, right? So for example, right, Abe Lincoln never told a lie. If we go with that, what that means is that Abe Lincoln always meant what he said, right? And so if we make D, the domain, things that Abe thought, and then we make P of x equivalent to Abe said x, and Q of x equal to Abe meant x, right? This statement right here is equivalent to what? What's the statement equivalent to in terms of what we defined here?
For all x and d, q of x implies p of x.
So here's where you have to be a little careful, right? Because I kind of set out of order specifically to have this conversation. So
Okay.
for all x and d, see, these are teaching moments. You think they just happened? No, they're made in a factory. They're made in the factory of my mind. The point is, so Abe Lincoln always meant what he said, right? If we're trying to deal with this statement, does P of x imply Q of x, and Q of x imply P of x? If we say Q of x implies P of x, what that means is that whatever Abe means, he says. But this isn't saying that he always said what he meant. This is saying he meant what he said, right? Saying that Abe Lincoln always meant what he said means that if he said it, he meant it. It doesn't mean if he meant it, he said it. Maybe there's a bunch of things out there that he meant, but he just kept his mouth shut. You see what I'm saying? This is only making a statement about things he said. Does that make sense?
Yes.
Awesome. So let's say for all px, if Abe said it, then he meant it. Right? And let's just say true. Assume this. Right? So this is a universal conditional statement, right? But for all x and d, Q of x implies P of x does not have to be true, right? Abe does not need to say everything he means. Every thought that he believes, he doesn't have to say. So the point is, this statement and this statement are not the same. We found an example, right, of a domain with these predicates, right? We found an example of a D, a P of X, and a Q of X, where the conditional is not equivalent to the converse. So in general, right, these two statements are not equivalent, but sometimes they will be, right? I mean, for example, if we were to say, or first of all, does this make sense? It's a little confusing. Probably shouldn't use I think I used a Dr. Seuss quote, but but yeah. Fourscore and 7 years ago. I wish I knew the Gettysburg Address all the way through. Our fellows brought forth in this continent, new nation conceived in liberty. Something. It goes on like that. It's only like 200 words. It's pretty crazy. Like one of the most famous speeches of American history is like 3 minutes long. It's awesome. It gets straight to the point. I mean, I guess I can only name like 5 speeches in American history, but still. So for example, if we're looking for a specific particular case where they are equivalent, it's not saying it works in general, it's where they are, we could say, let's say for all X in Benet said Washington's for all justice is a good one. That's right. Where they want us about political parties. Who knew that would be an issue, right? Or you have Kennedy, where it's like we go to the moon and like this in this decade, not because it's easy, because it's hard. Oh, what a speech! I Have a Dream speech is a great American speech. That speech the president gives at Independence Day, another great one. I was just gonna say that. Yes, exactly, that Independence Day. Thank you, Toru. Thank you. Someone who knows what I'm talking about. Probably the best one, honestly. But anyway, so if we say for all X in I have it written down here. There we go. For all X in 13, 14, 15, X is even implies X is a multiple of 7. Is this true?
Yes.
Yeah, right? Looking at this particular domain, this is a true statement. Whenever X is even, it's got to be 14, so it's got to be a multiple of 7. This is true. How about for all X in 13, 14, 15, X is a multiple of 7 implies X is even.
Also true.
Also true. So in this particular case of this particular chosen domain, these particular chosen predicates, right? This and this, the universal conditional and its converse, have to be equivalent, right? They have to have the same truth value. But in general, it's not equivalent. That's the point. In general, it's not the same. Sometimes it will be. Sometimes they'll be the same. Sometimes they'll be different. You just can't always say they're the same. All right. I feel much better about that. How about you guys? Well, luckily, I feel good enough for all of us here. Which is how many people? What do we got today? Oh, we're not doing bad. I feel as good as like 7 people combined. All right, so moving on. Good. Yes. This is a good topic. So now we're going to get to multiple quantifiers, thing we left off last time. Before we do, we need to talk about these. Well, first let's talk about sets, because we've kind of been dancing around sets. We've been flirting with sets. Let me give you guys a loose definition we can at least deal with. So sets are, or a set, I should say, is a collection of elements. That's it. Just a collection of things. Specifically, though, everything, and I mean everything, is either in or out of a set and that is all that matters. Specifically, order is irrelevant. Chaos reigns supreme. No, order is in like the way things are ordered.
Professor, I have a question.
Yes.
Do we have diagrams related to set, or it's just the writing?
Oh, yes. We do have diagrams related to sets, and there's a whole set theory chapter we're going to deal with later. So I'm just going to give you the basics. But yeah, so sets are always denoted with curly brackets. This will help. This will come back. So an example of a set is 1, 2, 3. All right, that's a set that just contains the elements. Got it. That just contains the elements 1, 2, and 3, right? Or you can have the set that is R, and that is the set of all the real numbers. Or you can have the set that's the set of, you know, like all matrices with real numbered components. For those linear algebra cats out there, right? So these are just sets. Like whatever's in curly brace, it just tells you all of these things. It's the collection of items. Now, what I mean by everything is either in or out of a set, and that's all that matters. What I mean by that is a set, you can think of it as it is kind of like, imagine, this is gonna be weird. Imagine everything, like literally everything. Imagine every single goat, like every single goat, every single planet, every single number, every single matrix, every single possible human being that could ever exist, like every single thing in the real world, in the imaginary world, everything, right? Everything that we could possibly put a name to, right? A set is just a collection of those, or just picks out these are the ones we care about. It's just like kind of partitions those and goes, these are ours. These are the ones we all care about. And so importantly, what that means is that, for example, 1, 1, 7, 6, 2, 2, 6, 5, or something like that, right? That set. Remember, a set, it just cares about every element being in or out. It has no concept of order, and it has no concept of if something's in it twice. It doesn't matter. So even though I have 1 written here twice, and I have 6 written here twice, it doesn't matter. All this means is this is the collection that represents, this collection represents the thing that has a 1 in it, a 7 in it, a 6 in it, a 2 in it, and a 5 in it. That's all. So this is the same as 5, 2, 6, 7, 1. Right? It doesn't matter. These sets are kind of describing the same thing. It's just the collection where these particular elements are in it. They just took the entire world of possible things and just picked these out. That's a set. Any questions? And after class, we can talk about set paradoxes all day long. I'd love to. But anyway, there's technically a couple of extra stipulations that matter to shore up some giant holes in math. But that'll show up later. That's not going to show up in our basic examples. You have to do something really convoluted to break math in that way. By break math, I mean actually break math. I mean the axioms that we assume to be true lead to a statement being both true and false, which should not happen. But anyway, so I'll talk about ordered pairs. This is the main thing we talk about, ordered pairs. So let A and B be sets. And then we could say, we can kind of label them. A is A1, A2, A3, like that. B is B1, B2, B3, like that. It could be infinite, it could be finite, doesn't really matter, right? Then A cross B is the set of ordered pairs AB, where A is in the set A and B is in the set B. I.e., another way you can think about this is A cross B. You could write it like this. It's the set of all AB such that A is in A and B is in B. That's the way you can write it. We'll talk about set notation later. Or another way you can think about it, in our particular example here, is A cross B. So it's gonna have A1, it's gonna have A1, B1 in it, right? Because that's one example of a pair from A and B. Another example of a pair from A and B is A2, B1. Don't forget A1, B2. Don't forget A1, B3. Don't forget A3, B1. Don't forget A3, B2. On and on. All the possible pairs you can make, right? Where the first coordinate comes from A, because A is listed first here. The second coordinate comes from B, because big B is listed second. That's the ordered pair. That's all it is, right? Like whenever you write parentheses around two items like that with a comma in between, that's an ordered pair. And it's called, it's an ordered pair because it's a pair of things, right? It's an ordered pair because XY is considered different from YX. And again, notice this is in general, right? So if X and Y happen to equal each other in that particular case, well, sure, this will be the same. But in general, XY is not equal YX. So, example of this would be if A equals 1, 2, and the matrix 1, 0, 0, 1, and B equals pi and E, well then A cross B would be the set. It's going to have 6 elements because there's 3 in here and 2 in here. And so you have 3 choices for the first coordinate of an element and 2 choices for the second coordinate. It's going to be 1 pi, 1 E, 2 pi, 2 E, 1, 0, 0, 1 pi, 1, 0, 0, 1 E. Make sense? It's order pair.
Quick question.
Hit me.
So, like, I guess an observation that's worth noting, right, is that multiplication of sets or crossing sets is not commutative, right? Because of the ordered pairs.
Ooh. Excellent question, Alex. Talk to me after class.
Oh. Okay,
Um,
and I think
guys,
one other kind of quibble is like it's more correct to say there's only 6 unique elements, right? Because you could have repetition.
yeah, sure.
Okay, cool.
This is actually bringing up some excellent points about identity and things like that, right? But yeah, there's 6 unique elements for sure. Like you could also represent 2 pi, right? You could write this as 1 plus 1 pi, right? Does that make it a different element because you listed it differently? There's like equivalence principle and stuff like that. Like in a certain sense, we think of 2 things that are equal as being the same thing. And so it's like, if you ever listed something twice, you just listed the same thing twice. It's kind of like, it's not like you listed 2 things that are equal, you listed the same thing. Oh, that makes any sense. But anyway, yeah, talking after class because it gets into isomorphism, but it's actually interesting. But anyway, so these are ordered pairs. Another example, is anyone taking linear algebra?
Hey,
Is that, who's that? Was that Afro?
yes.
Afro, okay. Oh, Alex raised his hand, nice. So you guys have probably seen this symbol right here. It's like the real numbers squared.
Yeah.
Has your professor talked about what that means?
No, not yet.
So the real numbers squared, the reason that's squared is because it's literally the real numbers cross with the real numbers. It follows the same notation as actual numbers, right? Like repeated multiplication as an exponent. Same thing here. The real numbers cross with the real numbers gives you r squared. And all this is all pairs
Real numbers?
of real numbers a, b, where a is a real number and b is a real number. Here, the two sets happen to be the same. And that's all it is. It's all pairs of real numbers. That's what r squared is. And that's why it represents the plane. Because if you think about the xy plane, here's x, here's y, this is really just a collection of the collection of all of these points. Like imagine if I was able to do this dot uncountably infinitely many times, right? And do all these points in the plane. And what's each point? Each point is just has an x value and a y value where the x and y are real numbers. The plane is just the set of all x and y real numbers. It's the same thing. It's just a way to draw it. Fascinating. Sets, man. These are sets. Order pairs, all that. Any questions?
I have a quick question.
Yeah.
Is a set of an infinite amount of the same number equivalent to the set of just that one element? It's like a set of an infinite amount of ones equal to just the set of one.
Yep, because all a set does, right? All a set does is it's a collection of things that are either in it or out of it. And so you just ask the question, is one in or out? It's in, right? So having it multiple times doesn't really change anything. It's just like, it's like the way we list sets in our human world, we write things down so we can see which ones are in or out. But yeah, so it doesn't matter if we put two there, it's just saying it's in at once. Good question though. All right. If anyone knows how to code in Python, ordered pairs are tuples and sets are sets. So some things make sense. All right. But on to the reason that we all care, discrete math. Specifically, multiple quantifiers. The thing that gets me out of bed in the morning, or at least this morning, so I can make this lecture. So, let's recall what the point of quantifiers is, right? Recall that quantifiers, they allow us to make predicates into statements. They make statements out of predicates. By claiming a certain quantity of the domain makes the predicate true. That's the whole thing. So our predicates aren't statements, they have a variable, or multiple variables, right, that we need to fill in to make statements. But quantifiers say, for example, you could have for all x and d, p of x is true, or there exists x and d such that p of x is true. This claims all the domain, the entire domain, makes p of x true. This claims at least one element in domain makes p of x true, right? That's what quantifiers do. Okay, and by the way, you could theoretically define more than this, right? You could define a weird there exists quantifier, I mean like there exists two or something like that, right? Or you could be like that like all but one or something. You could define that quantifier. It's just that we found these quantifiers to be very useful, and all other quantifiers can really be made out of these. Just kind of like how and or are two operations. There's more operations, but really everything can be made out of ands and ors and stuff like that. So those are the ones we're going to focus on. They're kind of the most elemental ones. All right. So that works great for a predicate with one variable. But what about predicates with two variables? So what I mean is, for example, what if we have a predicate R of UV to equal U plays on team V. And we'll call the domain for U, we'll say that's all-star basketball players. And the domain for V, I don't know, 4 teams at random. Let's just say the Lakers, the Nuggets, the Celtics, and the Heat. A bunch of storied franchises and the Nuggets. By the way, did you guys know the Nuggets, right, came from the basketball league, the ABA, which was that rival league to the NBA that existed like the 70s. And that's the league that invented the three-point line, by the way. And then there was a merger that brought in the Nuggets. But particularly, the merger did not bring in a team that I care about. That's called the Virginia Squires, which was based in the Tidewater area of Virginia. The point is, we could have had an NBA team, but they didn't make the freaking merger. They took the money, they dropped out. So now we have to root for the freaking Hornets or the Wizards. I hate both of them. But anyway, the point is, yes. So we have this example. This is a predicate with two variables, right? I mean, you can have a predicate with as many variables as you want. But, I'm sleeping on John Wall stuff. John Wall. And then the next example would be, let's say, Q of AB, where...
Professor, a quick question.
Yes.
Are we using set to do multiple qualifiers, as in like DU is also, sorry, DV is also DU?
No. So DU this is the domain for the U variable. So I have two variables here, right? U plays on team V. And whenever a variable on a variable on a predicate, we have to kind of define what space that variable lives in for it to make sense. And so I'm defining our domain for U, for the players, to be the all-star players. And I'm defining the domain for the team to be these 4 teams. So they're different.
DV is the big picture and DU is the smaller picture? As in like DV is inside DU or DU is inside DV?
Oh, neither. They're just different.
Okay.
They're just different, right? So these are teams and these are players. So kind of different things, right? I mean, we like I could have said, for example, X person eats Y food. And the domain for X's would be some people, like whatever domain you want it to be. And the domain for Y would be whatever domain of food you want, maybe just sandwiches.
Okay.
We're going to Scooby-Doo movie today. I want to make a giant cartoon sandwich after this. Anyway. So so QAB, and we'll define the domains for that later. But the point is, right, sometimes predicates have more than one variable. And here's the thing. If you're going to make a statement, right, from a predicate with more than one variable, what do you need to do? For example, like if you have a predicate with one variable, to make a statement out of that, you need to quantify how much of the domain you're claiming makes the predicate true. But for two variables, what's the extra bit? I mean, we say quantity of the domain, but which domain?
Of both, I suppose.
Both. Exactly, right? It's a good color for this. This will work. To make, that's not useful, statements. To make statements out of predicates with multiple quantifiers, or sorry, with multiple variables, need to quantify how much of each domain and in what order makes the predicate true. So, predicate with one variable, I just need to quantify how much of that one domain we're claiming makes the predicate true. Two variables have to quantify how much of both the domains make the predicate true. So, for example, maybe writing it down makes sense. And so we really have, I'll use the sheet of paper, statement paper. So we really have, for two variables, we really have three options, and we have a chat. We can talk basketball after class, Safa.
Straight.
Yeah, so there are 6 options to quantify P of X, Y with the for all and there exists quantifiers. And I should have made this sentence start over here. My bad for that centering. But the point is, they are 1, you can say there exists an X and dx such that there exists a Y and dy such that P of X, Y. Or you could say for all X and dx and for all Y and dy, we get that P of X, Y is true. Or you could say exists an X and dx such that for all Y and dy, P of X, Y is true. Or you could say for all Y and dy, there exists an X and dx such that P of X, Y is true. Or, right, so both of these, so these are kind of the homogeneous ones. Here's where we can start to mix them. And both of these have there exists X and for all Y in different orders. It's gonna matter. But also, what if we say for all X and dx, there exists a Y and dy. Is that P of X, Y? Is there two chats? Exactly. Wow, that was a nice name I had. Yeah. You can chain them together in any order. I'm just listing them to, I guess, for posterity's sake. It's like, I don't know, we keep all the seeds in the seed vault up in the Arctic, just in case. Yeah. So these are all we got. These are down the piece of paper because I've referenced this later. Any questions on kind of where we're going with this? Like, we needed to quantify both the X and the Y to figure out what things we can plug into P of X, Y, and have it be true. Okay, then we press forward. And when we press forward, let's first work. We're going to talk about each of these. Let's first work on number 1. We talked about last time, but now we're kind of looking at it in a slightly different way. So number 1 is double existentials, is what I'll call it. And that goes like this. The general form is there exists an x and dx such that there exists a y and dy such that p of xy. That is the general form. So, using our example here, let's make an example. So, for example, we could say that there exists a U in DU, the all-star players, such that there exists a V in DV, Lakers, Nuggets, Celtics, Heat, such that R UV is true. U plays on team V. So the way you write that in English is you'd say, there is an all-star player playing on one of these teams. That's what this statement means. This statement's saying that there exists a player in the all-star players instead of all-star players, such that there exists a team in these teams where that player plays on that team. So what that means is there's an all-star player playing on one of these teams. Make sense?
Could they be playing on multiple teams?
No, well, like in real life, you can only play on one team, right?
Well, yeah, but like with the context
right?
of
Like-
basketball removed.
What? Yeah, but with basketball removed, this isn't saying that there's not more than one all-star player playing on more than one of these teams, right? It's just saying that there's at least one all-star player playing on at least one of these teams.
Okay, cool.
Right? Okay. So, and here's the thing to note. Let's talk about this is gonna be our claim. This is our claim right here. This is true. But how would we prove it? And here's the thing to notice. Let's go ahead and let this right here equal what I'm going to call P with a little squiggly on top, X. Notice P with a little squiggly on top, X, meaning there exists a Y in dy, so this is a P of xy. This is a predicate, right? If you plug any specific X in here, if you plug any specific X in here from X's domain, dx, this will be a statement. It's an existential statement, but it's a statement. So this is just a predicate. You plug any X in, this becomes a statement. So this right here, there exists an X in dx such, it's really cool, there's this X in dx such that little squiggly, I'm not saying not px here, that's just like the thing of a p is to kind of make it seem different. Yeah. This is just an existential statement. This is just an existential statement where the predicate happens to be another existential statement, kind of. So, how do you prove an existential statement?
Find a true example.
Exactly. Or actually, not even a counterexample. It's just an example, right? To disprove it for all, you find a counterexample, because if I find an example counter to what the claim is saying, but to prove there exists, we're just saying there exists one. Let's just find the one that exists. So proof. Yes. Proof. Let U equal LeBron James. You might have heard of him, Safa. And then,
Nah, who's the?
and then the second best basketball player of all time. Second.
Yo! First!
So then let U equal LeBron James. We watch a show. So now this I'm gonna call squiggly R with a U. Right, it's a predicate once you play anything there. Watch a show that R of LeBron James is true, right? Because this statement is just equivalent to there exists a U and du such that R, well, squiggly of U. Just an existential statement. For an existential statement, we get to define one that satisfies the predicate. So we think LeBron James satisfies the predicate, so we just want to show that LeBron James does in fact satisfy the predicate. But R LeBron James, notice R, I'm just gonna call him LJ, is itself an existential statement. So we're kind of nesting these existential statements. That is itself this statement right here. There's just a V and dV says that R UV. So we need to show this is true. How do you prove an existential statement true? Find an example. So now we need to find example of V such that example of V in dV such that R of LJV is true. Because once we do that, we've proven this existential statement true. This existential statement is R squiggly U, which is the predicate of the whole thing. And so then we've shown that there exists a U and du that makes this predicate true, so then the whole thing's true. Just wait till we get to triple quantifiers. Actually, we're not even gonna do that because it's all the same. But anyway, so we have this. So then what's a V, Safa? What should V be?
The Lakers.
Exactly. Let V equal the Lakers. LeBron, for all these non-basketball fans, LeBron James plays for the Lakers. I'm let V equal the Lakers. Then, notes. LeBron plays for the Lakers. So R of UV, where U is LeBron and V is the Lakers, is true. Thus, there is a player. Oh, here we should note LeBron James is an all-star. That's important, right? Because our U had to come from DU. And remember, DU is all-star players. So, thus there's a player in DU that plays on a team in DV. Done. So I hope you see here that we didn't really do anything new. All we did here, exactly. Whoops, is Benet. Basically, just prove them one by one and use that chain to finally prove the statement as a whole. Exactly, right? So we need to prove this. So we need to prove this statement, which is an existential statement with this predicate. So we need to find something in this domain. We can plug in this predicate and make it true. So we found LeBron James, but now we had to prove that makes the predicate true. And to prove this makes the predicate true, we have to prove this statement true. And so even if there was 1,000 there exist statements, we could do this. I mean, it would take a while, but it would be just as easy conceptually. You have to prove that next there exists statement, the next one, the next one, the next one, until we get to this. Any questions? Oh, right. Let's talk about disproving real quick. So let's say we say instead, there exists an A in 1, 2, 3, such that there exists a B in 4, 5. With A times B equals 0. So this right here, that's what we call the predicate QAB. So I'm going to call this to be Q squiggly A. Now if you plug A in, this is an existential statement. Is this true or false?
False.
False. Right? Because no matter what we put from here, and no matter what we pick from here, you multiply them together, you're not going to get 0. So there does not exist an A in 1, 2, 3, such that there is the B in 4, 5 with A times B equals 0. So how do we disprove that? How do you disprove existential? Because remember, this is just an existential. This is equivalent to there exists an A in 1, 2, 3, such that R squiggly A. So how do you just
exhaustion?
method of exhaustion? Exactly, right? You have to show that for all A in here, R squiggly A is not going to cut it. R squiggly A is going to be false. So to disprove, all I have to say is let A in 1, 2, 3, then A equals 1, A equals 2, or A equals 3. If A equals 1, then, okay, in the case where A equals 1, we're trying to show that this is going to be false. We're trying to show that this little predicate here is false for any A you plug in. That's what makes this existential statement to be false. So we want our R of 1 to be false. How do we do that? Well, this is an existential statement. Now we have to prove that this statement's not true. So how do you prove an existential statement false? You have to show for everything in there, for everything in the domain, it makes the predicate not true. So, all right. B can equal 4 or 5. If B equals 4, A times B equals 4 times 5, which equals 20, which is not 0. If B equals 5, not 4 times 5, I'm sorry, 1 times 4. If B equals 5, A times B equals 1 times 5, which equals 5, which is not 0. And then you do the same thing for if A equals 2, And the same thing for if a equals 3. And then thus, and on like a test, you're trying to actually write this out, but I'm just trying to save time here. Thus, by method of exhaustion, right? There does not exist an A in 1, 2, 3 such that there exists a B in 4, 5 such that A times B equals 0. How do we know? Because we checked them all. So again, exact same thing. All we did here is really just disprove an existential statement where the predicate happened to be another existential statement. That's fine.
I have a question.
Yeah.
So I guess it's just like the observation that like method of exhaustion is not particularly efficient. And
No.
in this case, you could say something like, well, you can see that it's necessary if A times B equals 0, it's necessary that either A or B or both are 0. And you can see that 0 doesn't exist in either domain. And you can
Yep,
make a
and that's
proof that way, right?
you're totally right, Alex, and that's coming
But
up.
how would we? Oh, okay.
That's coming up in section 4.1.
I see.
Oh, glare part for yeah. Sorry about that. All I'm saying here is that do the same thing for 2, same thing for 3. You're gonna get similar results. Okay, so real quick, before I leave you, the punchline, which is gonna be the same thing we said last time, but last time I was rushed. I hope this makes more sense now. And that is that where's my thing? There we go. Yep. Okay. In general, I'll start here. In general, the negation of there exists x and dx such that there exists y and dy such that p of xy, what's that going to equal? Well, remember, we can call this is just square root of p of x, right? This is just a predicate. It happens to be existential, but it's just a predicate. So this is the negation of there exists x and dx such that that. But now we're going, we know how to negate existential statements, right? The opposite of there existing in x and dx, such that we get this p thing, is that for all x and dx, we don't get the p thing. And then now we can start to remember what this p squiggly actually represents. This represents there exists a y and dy such that p of xy. But hey, we know now how to negate existential statements again, right? This is for all y and dy, then you negate the predicate, not p of xy. So the negation of this is this, just by following our rules. Nothing too special there. Know your rules. You got to know your rules. Yes. Okay, so so the piece of resistance, there exists x and dx such that there exists y and dy. What time is it? Okay, sorry guys. Such that p of xy, right? What does this really mean? this means you can find an x and a y such that p of xy, right? So this means there is an x, y pair with x and dx and y and dy such that p of xy equals true. And what's it mean for there exists y and dy? Does there exist x and dx such that p of xy? Well, same thing. That just means there is some y and is some x where p of xy is true. So this means there is an xy pair such that p of xy is true. So they're the same, right? They're both just saying we can find an x and find a y in these respective domains that makes p of xy true. But if we write it like this, the one marker I wanted, if we write it like this right here, what is it also equal to? These are both also equivalent to, how else can we think about this? If I translate this directly, what's it saying? There exists a what? The green part.
Could you say there exists an ordered pair xy in the sets dx cross dy?
Exactly.
Yeah.
If I'm saying there's an xy pair, well, xy pairs live in what? They live in this domain dx cross dy. Dx cross dy is just, remember, the set of all ordered pairs where x is in dx and y is in dy, right? So I'm saying that there is an ordered pair with x and dx and y and dy. It's exactly saying there exists an xy and dx cross dy, such that what? P of xy. Boom. So what's that mean? What it means is this double existential statement isn't really anything new at all, right? Because this is a domain, right? You can think of this as a domain. You can think of this as an element, right? So this is we can rewrite this as a single existential statement. So we could think of it as a double quantifier, multiple quantifier statement, or we could think of it as a single multiple quantifier statement where elements happen to be pairs. So it doesn't really matter. The point is, though, lots of ways to think about it, and we will do the rest next time, and possibly get into, probably get into 4. Oh yeah, we should get into 4.1. So we're kind of going at half classes now. We'll get it fixed. But anyway, that is class. Sorry for going over. Any questions?
Wait, so does the commutativity thing not come up in like the other case where you've written it y first and then x?
Good question. So right here, even though I've written y first then x, at the end of the day, I'm still saying that this y and this x makes p of xy true. So I could also think about a pair yx, or I can think about the pair xy. I'm just saying there is an x and there is a y, and there is a y, there is an x that makes p of x true. So like for example, if I have this statement, if this statement's true, that means there is an x and there is a y. Just take that y and take that x, plug them in here, and it'll make this statement true.
Right, right.
Yeah. Oh, is there a chat? Is there 3 domains? Does the cross of those domains lead to x, y, z? Exactly, Benay. Exactly. If you have 3, if we have a, like, either there exists an x and dx, there's a y and dy, there's a z and dz, there's that p of x, y, z is true. Well, again, you can just write that as there exists x, y, z, and dx cross dy and d cross dz, such that p of x, y, z. So we're going to find out with these double existential and double universals, we don't necessarily get anything that interesting. It's the mixed quantifiers we start to get cool stuff. And the crosses are essentially just permutations within the domains, right? So class is over, by the way. I'm just answering questions. Now it's time to get weird, fun, and technical. So this is probably with the recording in. So if anyone wants to leave, go ahead. Well, you can always leave. But thanks for class. It was awesome. But so there's permutations within the domains, right? So across the domains. So technically, the reason I'm hesitating, Vinay, is because technically a permutation, like we'd say that 1, 2, we'd say that like 1, 3, 2 is a permutation of 1, 2, 3. Technically, permutations are just the same things in different orders. Yeah, no,
I think it's like pick one
combination-
from each domain, right?
Yeah. No, combination I'm more down with. Yeah, it's a combination of specifically one from each group, which is exactly why, by the way, that if the bars around a set mean size, like if A equals N and the size of the set B equals M, the size of A cross B will be N times N, because you can think about it like if A is, like, to use a classic combinatorics example, if A is like, I have 3 pairs of socks, and B is like, I have 10 shirts. I don't know why my number of shirts way outnumber my number of socks. You think about the number of pairs, the number of combinations of socks and shirts I can make, it's gonna be 3 times 10, which is 30. Right, because you know, I can have the first pair of socks and then I have 10 options for this shirt. The next pair of socks, 10 options for this shirt. Third pair of socks, 10 options for this shirt. So in total, I have 10 plus 10 plus 10, which is 3 times 10 options for this shirt. But yeah, that directly corresponds to ordered pairs. Does that make sense?
But aren't you like saying order doesn't matter because like it's a combination, and whether it's sock pants or sock shirts or shirt socks, right? It kind of. Can we talk about this commutativity thing?
Yes, we absolutely can. So, great question, Alex. So the question is, if A and B are sets, does A cross B equal B cross A? And it all comes down to what you mean by equals. Strictly with an equal sign, they don't equal each other. And an easy way to see that is like if A, for example, is the set, like if A, for example, is, you know, the set of like some matrices, you get like 0, 1, 0, 2, 1, 1, 2, 2, 2, 3, 4. Like it's just some set of matrices, right? And then B is like the real numbers. Well then, so what it means, so we're gonna go over all this, but what it means for two sets to be equal. So to say that like set S is the same thing as set T, what that means, and we can use this arrow, this means, this literally this arrow is being used correctly here. This is this is like a bijection, but with predicates. What this means is that S is contained in T, and T is contained in S. And what's that mean? Well, S contained in T, this means for all X in S, X in T. This means for all X in T, X is in S. So now we're getting deep in the definitions here. So the problem with this is that, like, let's prove that A cross B doesn't equal B cross A. Well, if it did, I need to show for all X and A cross B, for any element of A cross B, it's got to be an element of B cross A. Well, note note that 1, 0, 0, 1, and 5 is in A cross B, but not in B cross A, right? Because in order to be inside B cross A, what you would need is in order to
Real
be
number, then
what you
matrix,
need is the
right?
first element to be a real number and the second element to be a matrix, which is not what we have here. So thus, A cross B is not inside B cross A. So specifically, A cross B does not equal B cross A. So you're totally right about that. I feel like that's what you were thinking before. The reason I give it a little bit of pause is just because in math we also have this idea called isomorphism. And in isomorphism, well, it depends what you're talking about, but firstly, it's got to be a bijection, and it's got to, or they got to be bijective. And so a bijection between two sets. So if you say that loosely, if you say that like S and T are isomorphic, right? What that means is that we should be able to line up the elements of S and T in a specifically nice way. And so if S, you've probably seen this before. If S is like the elements like A1, A2, A3, A4, and T is like the numbers, or I'll say if S is A, B, C, and T is 1, 2, 3, 4, there's no real nice way to line it up. Like A, you can put A with 1, B with 2, C with 3, but 4 is always going to be left by itself, right? There's no nice way to line these up. Isomorphic kind of means that these two things are the same, they just look different, right? But if they're the same, they look different, we should be able to correspond every element in F with every element in T. But we can't do that. We can't correspond 4 with anything. And then same thing, like if there was a D here, right? We couldn't correspond D. I mean, we could correspond D with 3, for example. But now 3 is being hit twice and stuff like that. So, and if you had more, you have this, so it sounded like that, right? But the point is, we're not uniquely corresponding elements in S and T. The way uniquely correspond elements in S and T is if there's the same number of things, then we can correspond them nicely. And so if you're dealing with finite things, then you could just say that. But we like to deal with infinite things. And we deal with infinite things, we can't just count them. So what's it mean to have this correspondence? Well, what it means is, notice that the only way this correspondence fails is that either there's something left over. So I'll say correspondence fails if something in T is left over, or if two things in S mapped to the same, or correspond, I'll say, to the same thing in T. That's the only way it fails. If everything in S corresponds to a unique thing in T, and nothing in T is left over, then you're good. So everything in S corresponding to, so everything in T getting hit, like corresponding to something, even if two things go to it, this is called being surjective, or it's called being onto. So like this would be onto. Everything gets hit. Whereas this correspondence wouldn't be onto. Now notice you could make it onto by doing that. That's a different correspondence. This particular correspondence here is not onto. This one is, because everything gets hit on this side. Now,
so this is like the kind of idea of like you need to be onto and one-to-one, right, in linear algebra.
you know it. There you go. Yeah. Exactly. This is exactly what we're talking about here. You need to be onto and one-to-one. So this is what it means to be onto, and then one-to-one just means you don't have two things one of the same thing.
Yeah.
It would not be one-to-one. It would be onto. Now, if we were able to have another element here, and then we did this, well, this is one-to-one. But like if this wasn't here, this would be one-to-one, but not onto. So one-to-one takes care of this, and being onto takes care of this. So S and T are isomorphic if there is a one-to-one and onto correspondence between S and T. If we can find one of these correspondences that work this way. So A cross B and B cross A, in this particular case, right, let's define a correspondence. Let's say that like any A cross B in here, we're going to send that to BA. Now, here's the question. Is it onto? Well, take any, I'll call it B prime, A prime, any random element in B cross A. Then notice AB is an A cross B. And AB does go to BA, B prime, A prime. So the point is everything does get hit. It's onto. Good.
Mm-hmm.
Now is it one-to-one? Well, let's assume that A1 and A1 B1 goes
B1 A1, right?
How do you show this? Assume A1 B1 goes to the same thing that A2 B2 goes to, and let's call it B prime A prime. Well then, by this correspondence, that means that, remember, A1 B1 we know goes to B1 A1. So B prime A prime equals B1 A1. In particular, B prime equals B1, A prime equals A1. But we can do that with A2 B2 too. So you get that B prime also equals B2, and A prime also equals A2. Meaning A1 must have equaled A2, and B1 must have equaled A2. The point being,
so there's only one mapping.
there's only one element that goes to that, right? You can't even conceive of two that go to it, because if there were two that went to it, you prove they're the same. So it's one-to-one onto, meaning we have this really nice correspondence. Meaning it's essentially the exact same thing. That's a long-winded way of saying that. It's essentially the exact same thing. And that it behaves in the same way and stuff like that. But it just depends how you want to look at it. It depends if you want to look at equality or isomorphism and things like that. And like one place where you might, like this isomorphic thing might seem like just a weird construction, But I mean, a place where it might make a lot of sense is, let me think. If you're looking at, so well, this is where things get weird. I'll just put it this way. Technically, the integers are defined by the Peano axioms. And so, or, this isn't a good example. We kind of have to get in some abstract algebra to show how useful isomorphisms come in. But the point is, these things are basically the same. They act the same. They just kind of look different. So are they different? Well, that depends how you look at it.
So is this like the direction where you go and show that there's like isomorphisms between like the reals and the integers and stuff like that, and
Yeah.
but not between irrationals or something?
So what we can show is we can show that the natural numbers are isomorphic to the integers, so include the negatives, and both these are isomorphic to the rational numbers, so all fractions. This is the weirdest hell fact right here, that all the natural numbers can be put in correspondence with all the fractions. Like the naturals to the so if we look at like just the natural numbers, which is these, and if we look at all the integers, right? We kind of correspondence nice and easy. It's not that hard. Like let's say 1 goes to 0, and then 2 goes to 1, 3 will go to -1, 4 will go to 2, 5 will go to -2, 6 will go to 4 or 3, 7 will go to -3. We kind of keep going on like that, switching back and forth with the next one here, 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 here. You kind of see that makes sense. But I mean, the freaking rationals. I mean, the rationals are like, you have 0, 1, 2, 3, 4, 5, of course, -1, -2, and -3, all like that. Then you got 1 here, 1 here, 1 here. Like every single decimal that repeats or terminates, you know is going to be one of these things. There's between 0 and 1, there's infinitely many rationals. So it's insane you can make this correspondence, but you can. Now, what you can't do is you can't make the correspondence to the real numbers. And the real numbers, you can't make a correspondence to the irrationals. So, yes. But the idea of isomorphism honestly goes past this, because these guys are different in a lot of ways. Like, these guys are kind of different sets. We can just prove that we have this correspondence, which kind of proves that there's like a certain sense the same number of them. Where things get really interesting is where you prove that two sets of things with operations behave exactly the same. So for example, you can prove that, I don't know if you know mod arithmetic, but mod arithmetic just means take the remainder when you divide by 2, or mod
Like
2.
clocks, right?
Like clocks, exactly.
Yeah.
And so the way you do that, so the technical way to write that is you'd write 0/2z plus. And what that means is we're looking at the elements 0 and 1, right? And then the plus is defined as, so z over 2z just has a 0 and a 1, and the operation is defined by 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and then 1 plus 1 equals 0, because it wraps back around. You can think
Right.
about like the last digit in binary addition.
Right.
So this is called a group. it's a set with an operation that works particularly well. It's defined this way. But you could also look at, for example, what is it? With, I think, and then we'll use regular matrix multiplication. And so this is another group. And then like 1001 times 1001, that just equals 1001. 1001 times negative 100 negative 1, what's that going to equal? That's going to equal, okay, negative 1, 0, 0, negative 1. And then negative 100 negative 1 times negative 100 negative 1, that's going to be, oh, sorry, wait. If we make this 0, 1, 1, 0, oh no, other way around, 1, 0, 0, 1, multiply that out, you get negative 1, 0, 0, negative 1 like that, right? This actually works, nice. And then if you do that, you get negative 1 times 1 is 1. You do the matrix multiplication.
And you get the identity back, right?
The identity back. Do you see how similar these two setups are? Wait, I should have. This happens to equal z over 2z. Yeah.
So there's a mapping between like the operations and the arguments,
Yeah.
right?
There's totally a correspondence here. 0 corresponds with the identity, and then 1 corresponds with this guy, negative the identity, right? But it also, it works like, the thing that really makes an isomorphism is not only the correspondence thing, it's the correspondence thing, and it works with an operation. So notice here that this correspondence totally works with the operation. Like 0 plus 0 is 0. Identity equals identity, right? Do you see what I'm saying?
Yeah.
Yeah. So, like, if you want to know, like, if you want to know what 1001 times negative 100 negative 1 times negative 100 negative 1 was.
You could take the transformation into 0, 1.
Exactly, you did the
with
transformation
plus
here. You go,
operator.
okay, wait a minute. What is 0 times 1 times, or 0 plus 1 plus 1? Well, 0 plus 1 plus 1, that's 0 plus 1 plus 1, which is 1 plus 1, which is 0. So then you take the transformation, you get.
And then you take the transformation back, yeah.
1, 0, 0, 1. The point is, you get this correspondence here that works over the operation. And that's key because, in a certain sense, are these even different things? Or is this just the same thing written a different way? Right?
So is this like similar to like, say, S transforms and like circuit analysis?
I have no idea what that's.
Okay,
That's where you'll lose me.
maybe like Fourier transforms then? I think that's maybe a bit more generally known.
Well, as far as I know, I'm not an expert in Fourier transforms, but Fourier transforms are just kind of a way to represent a function as a sum of sines and cosines. And if you actually take the infinite Fourier transform, or you have an infinite sum, it will be exactly equal as long as your functions follow some nice properties. So in terms of like writing the same thing in different ways, it's similar. But they're all in the realm of the same stuff there, right? Like, for example, writing 1 as equaling sine squared of x plus cosine squared of x. I mean, we are writing the same thing in 2 different ways, but at least like we're kind of still in the realm of numbers. Like the output of this will be a number that is 1. That's why we can put an equal sign here. But here we're in 2 different realms. Like 0 does not equal the identity matrix. one does not equal the negative identity matrix.
Hmm.
They both have the same structure. An isomorphism kind of abstracts a layer up from specific values and just pays attention to structure.
Right. So just like the types of elements and how they're related and the operations that act on them.
Yep. So, a very long-winded way of saying, if you think about it this way, A cross B is kind of the same thing as B cross A. If you think about it in the equals more, or the equals way, with that actual equal sign, like set containment, things like that, well, they're not the same. But they definitely have the same structure. Like it's kind of just the same thing with a different face, you know? But
Okay.
sometimes, oh, okay.
Sorry.
I have to leave you guys. But I enjoy this. Talking about these questions. Please keep them coming.
So what I'm hearing is I should find myself like an abstract algebra textbook.
Like this one? Or this one? Abstract algebra. What's your major, Alex?
I am an electrical engineer, which probably doesn't need to touch abstract algebra, but probably
If-
can't hurt.
You had the room in your schedule.
Uh-huh.
I would highly recommend that you take yeah. I mean, if this interests you guys and you have room in your schedule, I would highly recommend taking modern algebra, which is the 3000 level. It's basically abstract algebra. And that will tell you if you actually like it or not. But it's pretty fascinating. It's all about this structure kind of stuff. This is why mathematicians kind of leave numbers behind. That's why it's called abstract algebra, because actual algebra works on numbers. Abstract algebra is above that. It doesn't like it's not even so much it's not working on numbers. It just works on anything. It could be numbers, it could be matrices, it could be whatever. It works on any type of element. As long as it has certain structures, because the structures are the key here. But yeah, no. I mean, it's fun. Highly recommend. Or you know, you can just watch a bunch of videos on it. The only difference between watching videos and taking a class is that, you know, taking a class actually forces you to go and do the work and try it out yourself. And that's like for example, like if you see someone in a video, like myself, like right here, right, kind of doing something and to make it look easy, you might not understand why it's so special. But then when you actually go to do it, you see that it's hard, and then you see like a beautiful way to solve it. Then you actually understand, oh, this is a special thing we solved. This isn't easy. Three Blue, One Brown just came out with a fantastic video about the monster group. I actually don't.
Yeah, I saw that.
I don't like the way that he described groups as symmetries. It's kind of similar to what I was just talking about here, but there's some crossover there. I mean, I think he's technically right, and I think that's a way to visually show what he's talking about. But I don't think it's the easiest way to understand groups at all. I think the easiest way is just by the definition, even though it's kind of boring. It doesn't look pretty. I think it's easier, but the way he describes the monster group is like I actually never learned about the monster group. I've taken I've taken grad level like 2 years of grad level abstract algebra, and in 2 semesters, and we never touched the monster group or any of that. And yeah, so that was great for me personally. But yeah, guys, I gotta go. So but hopefully see you Thursday or whenever you guys come to class again, and have a good one. Have a good Wednesday.
All right. Take care, Professor. Thanks.
Thank you. You too.